during today's presentation, I'm going to talk to you about why should we work in space, how did we get started in this area, and what are some of the projects and research areas that we're working in within space robotics to transition some of that terrestrial technology for use in space. So why should we work in space robotics? We first started brainstorming this around 2021, 2022, and one of the first things we did was we called up our space sector, which was one of the perks of working at SwRI is that an expert in just about anything is just a phone call away. So we called our space sector and we asked them, what are some of the problems that you're seeing within robotics and automation for the space industry? What are your clients interested in? What are the types of things that we should be doing? And as we started listening to their answers and gathering their feedback, we saw a lot of parallels with the type of work that we do very well in terrestrial robotics. And so that launched our Space Robotics Initiative. Also, we're working in space robotics because space robots are cool. So how we got started, back in 2021, 2022, we were having a brainstorming meeting in our large workspace robotics program, which was run by Cody, who presented earlier today. And we were talking about what are places that we can put robots that we aren't currently putting robots. So where should we be expanding in these large, unstructured, challenging workspaces? Two things came out of that program area's discussions. One of them was the program that Cody talked about this morning with maritime robotics, and then the other one was space. The joke that I like to make there is that space is the largest workspace, and my workspace is larger than Cody's. So we've determined that robots in space are a good idea and are very cool. So now what? What do we do with, or where should we use robots in space? We broke this down into a few different technical areas that we see as having a lot of good overlap with the terrestrial robotics work we do, and I'll talk through a few of those now. So up first is robotic manipulation. So these are robot arms. You might be familiar with industrial robot arms that are used in automotive applications. There's also collaborative robot arms that are used to work closer to people. So what types of tasks would robot arms do in space? Well, if we look to our favorite Pixar movie, WALL-E, we'd say robot arms can hold hands. Okay, that's not quite right. What about trash pickup? This one is actually pretty close to reality. Space debris is a tremendous problem. There's a large amount of satellites and space trash in certain orbits that are becoming quite crowded. So even though space is this really large workspace, some places are still kind of crowded. And as we see more constellations being launched, launches getting cheaper, so there's a lot more launches, this is only getting worse and worse. So we need to be able to clean up the trash. What would this look like? So here's a concept rendering of what a robot arm might be able to do with some space trash. So it would fly up, reach out, grab the space trash, stow it somewhere, and then move along on its way to pick up its next piece of trash. From there, this spacecraft could either go out into graveyard orbit, or it could come back down into the atmosphere and burn up. So this is what we're trying to achieve, this type of thing. So how do we do that with terrestrial technology? We have a number of different pieces of technology that could be a really good fit here. So you might remember that Cody talked about scan and plan. That same type of technology is exactly what we need for understanding space debris and figuring out how to pick it up. So here's an example of an industrial application where we're looking at something, understanding the shape of it, understanding a complex surface, and making our robots move automatically without having to program it for each individual part. This is exactly the type of thing we need for space because we don't necessarily know what we're looking at up there, right? Especially with debris that's been up there for a long time or something that previously was one piece and broken into many pieces, we don't know exactly what the shape is. So looking at something, understanding what it is, and how to move the robot is piece number one. How we inform the robot is these raster paths that you can see here. So the sensor can give us a surface, and from there, scan and plan is able to figure out how the robot should move, so what those raster paths are, which is the graphic that you see here. But once we have an understanding of the shape of the object and kind of roughly how we're supposed to interact with it, we need to give the robot a sense of feeling so that it understands the real world differences, right? Robots work incredibly well in highly repeatable environments where everything is perfect. But the moment we're in the real world, that breaks down. And the moment we're in space, that gets even worse because we have free-floating systems, right? So we may not be able to know that something's not quite where we expected it to be, or maybe it's a little bit angled from how we expected it to be. If we are able to add compliance through adding force torque sensors at the end of our robot, we give the robot arm a sense of touch almost, so the robot can feel around, feel where it is in the process, and respond accordingly. But we still can't quite translate this to space immediately. There's another challenge that we need to think about. When we think about free-floating robotic systems, a lot of people think about the Canadarm on the International Space Station. So as the Canadarm moves around, it doesn't have too much of an impact on the space station because the space station is much larger than the Canadarm. There is a little bit of an impact, but not a whole lot. As we try to scale this whole problem down to be smaller and more cost-effective, which is what we need for debris cleanup, we need to suddenly start thinking about the physics of the entire system. Because as we're moving our robot arm around, that motion impacts the spacecraft that it's mounted to, right? So we end up with this tail wagging the dog situation. So this led us to study physics-aware motion planning, so completely changing how we go about doing robotic motion planning by thinking of the motion of each individual link and how that factors into the motion of the overall system. So you saw some simulation images on the last screen. How do we do that testing on Earth, right? So we have a Space Robotics Center in Building 290, which will be on the tour later today, so I hope you all will join us down there and get to see a demo of this system. This system allows us to move this robot arm, and this whole thing floats. The way that works is within that spacecraft, that black box you see at the bottom, it's our model spacecraft. There's an air compressor and batteries and computers and the robot controller, and that air compressor provides a small amount of flow to some air bearings that are underneath this platform. So this entire system is able to float. So it can float and translate in XY as well as rotate. And this thing weighs about 600 pounds, but you can tap it with your finger and it'll move when the air bearings are on. So using this, we're able to test microgravity along a plane, and you do some validation activities for our motion planning. So getting into hardware examples, why does physics-aware motion planning matter? So on the left-hand side, you can see a typical terrestrial path, and on the right-hand side, you see a kinodynamic path. So that is a physics-informed trajectory. You'll notice that the kinodynamic path gets a lot closer to where it's going because it's able to account for the fact that it's unconstrained at the base, and it's able to rotate and move. So if we look at this for a concept of operations like what I showed in the animation, that might look like something like this, and note this is sped up in the interest of time. So the robot takes a big motion using kinodynamic planning to get relatively close to its target. And at this point, it's switched over to closed loop control. It uses that silver camera that you see on top and tracks the April tag. And then it moves the piece of debris to a storage location. And then when it's done, it removes the robot arm. So I talked a lot about robot arms. Let's move into a couple other technologies. Advanced perception. So remember that debris problem. I alluded to this earlier, but we don't know what all of this is. Lots of this is being tracked. Lots of the big pieces are being tracked. But there's a lot of uncertainty about some of the older things that have been up there, or spacecraft that have broken up, or rocket bodies that have broken up from failed launches. There's a lot of stuff up there that we don't know the exact shape of. So we need to be able to look at something and really understand what it is and how it's moving before we try to interact with it, right? Because the worst case scenario would be we reach out to try to grab a piece of space trash and we accidentally break it into more pieces, right? That's just making the problem worse. So we've done some research around looking at something and seeing how it's moving. We actually pulled from our automated vehicles group for this work. There's a technology called SLAM, Simultaneous Location and Mapping. And typically the way SLAM works is it's a model of an environment as a vehicle moves through it. We flipped the narrative on that. So the observer is stationary, and we're assuming we're looking at something that's moving away from us. And we use the information from one frame to the next to determine how much something is moving, and how it's moving is plotted on the right-hand side there. So using this, we're able to know what we're looking at and how it's moving. Another area of research for us is off-road autonomy. Because there aren't roads on the moon or Mars yet. There are plans for doing exactly this. There's an area of research called in-space resource utilization that's looking at using the soil, so lunar regolith or regolith from Mars, and building infrastructure and building roads and building launch pads, which is fantastic. It's a really exciting future to think about. But right now, that doesn't all exist. So what we have now is we have an environment that kind of looks like some desert off-road environments that we've worked in. There's not a lot of features. There's some pretty significant hazards that we don't want to risk our expensive rover getting into. It's a lot of the same problems, right? So as you may know, we've worked in off-road autonomy for the DoD for many years now on a number of projects, including a lot of environments that look fairly similar to some of the environments that you might see in space. I always like to use the project in the top right-hand corner as a great example for why we should look to terrestrial technology when we're thinking about space applications. So this is showing a system called Ranger. It's a downward-facing camera with an array of lights around it. And essentially, it uses a fingerprint of the ground to do relative localization for an autonomous vehicle. This was developed for terrestrial applications. It was never, space was never considered at all when this was developed. But some of our engineers had the idea of, well, could we try this on regular simulant and see what happens? So once again, we called up our friends in the space sector. We took it down to the regolith lab, and we ran Ranger across some simulated regolith. So this is geometrically similar, so it has a similar texture and similar shapes. And it actually performed out of the box exceptionally well. So it's such a great example of when we're looking to do these advanced autonomous future plans in space, let's look to what we have here on Earth first. So our mission within our space robotics program is transforming Earth-based robotics capabilities to meet the current and future needs of the space industry. And also, space robots are cool.
Okay, taking questions for Meera, right over here. What size of debris would robotics be useful for removal and not exacerbate the problem?
That is a great question, because this is something that Space Force has looked at a lot for different scales of debris. So Space Force has had a couple of solicitations over the past 3 years or so looking at very, very tiny debris, but also looking at kind of mid-sized debris. So I'm gonna say somewhere in this range. I think that's gonna be where we go first. I think somewhere in this-ish size is going to be about where we go first, just because of the economics of the system, of launch, all of that. I hope we eventually move towards larger and some of the really novel concepts for capturing much smaller debris, but I think we're going to be in this kind of middle range first.
Okay, another question right back here. Do space robots consider the density and the makeup of the material?
That is also a great question, and we've looked at half of that, and we have another group that's looked at the other half of that. So in terms of kind of the density and the mass properties, we did look a little bit at that as, are there some big assumptions is maybe not quite the right word, but are there some bigger conclusions that you can draw about the inertial properties of something based on looking at it, right? Like you would assume that solar panels wouldn't have as much mass as the main spacecraft itself, right? So are there things like that that you can use to inform your motion planning and where you grasp the spacecraft? We have looked at that a little bit. In terms of material classification, that's not something that we've really incorporated into this at this point, but we do have a lot of research on that on the industrial robotics side. So it's certainly something that we could incorporate if the right project arose. But yeah, that is something that the industrial folks care about quite a bit. Yeah.
All right, let's take one more question right here.
Question about the debris field. So this thing is kind of a piece of debris and it's getting hit by other debris. How do you account for that?
How do you account for the debris field, the debris running into each other?
Or into the spacecraft?
Of the spacecraft.
So while the space trash problem is very bad, it's not quite that bad just yet, right? So there are ways to plan maneuvers and moving in to capture a piece of space debris without being at risk of getting hit. Right now, that is still doable. It takes some careful planning. It takes a lot of sensors on the spacecraft to make sure that things are as expected. But right now, it is still conceivable that that could work out. If we don't start working on this problem soon, that may not be the case anymore.
All right, thank you, Meera.